Today I want to show you the hollow clock V or 5, which I built, and the minute hand is controlled by this cog here. See the blue cog, and zoom and focus, nice. And the hour hand is controlled by this white cog, and the hour hand is on a magnet, and not a very strong magnet, but you turn the white outer ring and it turns the hour hand. And then those two cogs are pushed by these two cogs, is the hour hand and the minute hand, and the stepper motor. Let me just disassemble this. Let's tilt the camera down a bit. And I'll show you some cool code. Where's the opening? There. Screw on the bottom. We have to fast forward past the step. 2 screws here and here. Turning it the wrong way. And this big pad here that you see is 3D printed to hold the screws. Very handy. Okay, and open. So what I'm going to do, let me just show you real up close. So there's a Raspberry Pi Pico there, RP2040, the stepper driver controller motor, and the stepper motor itself. So let's have some fun and take out this stepper motor and put in this stepper motor, and there's the driver board for it, and there's my other Raspberry Pi with the debug probes on. I'll just pause the recording while I change it over. Actually, you might want to see that, so I'll just pull the motor out, take the cog off, and untwist all these wires to get it out of the way. If I could just take the whole thing out and put it aside, that's handy. And then put this motor back on. Just shove that one in there. Shove the cog on. Done. Ready to go. Now let's get some controller code working. So the current code is just turning it every second. I'll just plug that in. I have to hold the cog in place so there's no packet. There we go. Oh, you can't see. Let me zoom up. Tilt up. Ta-da! You can see the hour hand slowly moving. There's a bit of sellotape on it because to keep the magnet inside it. So the original writer had stepping with 8 milliseconds between steps, but I wanted to go fast, so I changed it to 1 millisecond. Watch what happens when I change it to 800. You'll see these stepper motor lights. It's saying this magnet, then that magnet, then this magnet. So inside the motor, let's have a look. There's 2 magnets. Let me show you. So inside the motor, I'm not sure how it works. I don't understand phases and coils, but I imagine there's an electromagnet here, an electromagnet there that can suck or pull a fixed magnet on there. So if you have this one on, the magnet will be pointing down. If you have them both on, the magnet will be pointing here. And if you have them both in reverse polarity, the magnet will be pointing there. So you have to go between a series of steps to say this one, then both, then just that one, then this one pull and that one push, and so on. And that's what you can see in these lights here. We're doing 800 milliseconds, so the hand is moving super slowly. I don't know if you can even see it. Let's have a look. Can see nothing. So every 800 milliseconds is moving 1 step, and as my understanding is, the gear itself has 64 steps to go around. And then with the other cogs, it's even more. So I'm sticking it. So what we could do is just make it run as fast as it can, just spin the clock around just for fun. And we'll go to our loop. So instead of calling every minute and going to tick it up next to wait, we're just going to go rotate. We don't know how many steps, we're just going to say, I don't know, 2048, which is, according to my test, was 48 minutes. So let's see how this runs. And we run. And the clock is now doing full speed rotation. Go, clock, go. Woo. You can't see the top end. I think I've broken it. There we go, it's good. Okay, so the issue I had at one point was that the stepper motor would jump out. I had to hold it in here, and even with the cover on, it was jumping out. And I fixed that by jiggling it, but now I fixed it by just putting the cover on really tight. Let's make it change direction each time. We'll do 2048 one way and then 2048 the other way. I'm guessing that's the milliseconds. I've got a set direction, which is here. So we've got set direction. Oh, the clock fell out normal. One for normal and one for reverse. And run. Put the clock back in. So it should run 4 minutes forward and then 4 minutes backward, according to my measurements. 4 minutes forward. Oh, you can't see it because you're looking at the back. Let's see. 4 minutes forward, and then it's not going backwards enough. It's because there's a ratchet in there, and the ratchet's stopping it. So you can see the ratchet right there. I might pull that ratchet out because I don't really need it. See, it's trying to hit. When it tries to go back, the ratchet's stopping it. Ratchet, stop. Wait, let me get the angle right here. Ratchet, stop. I'm going to take that ratchet out. Just pause the video. I want to do that. I get to show off my amazing cool tweezers. Shook. Tap out. Can I get it? I can't even get it. There you go. Out. So now there's no ratchet, so it should go 4 minutes forward and 4 minutes backwards. 4 minutes forward, 4 minutes backward. And how did I find out there was 4 minutes? I literally just typed in numbers. Now you can't see. Now you can see. And you can see the without the ratchet. It's just jumping off because I'm not holding it on. Hold in there. It's working hard. It does not like to go backwards. Clicking and clicking. Okay, so let's look at the code compared to the original code. So this is the code. This is the original C code, and they have steps per minute. I don't know how they worked out 2048 times 90. I don't know where the 90 comes from, but they have steps per minute as 256. When I put my speed at 8 milliseconds, see they're doing 8 milliseconds. No, they're not. Okay. So there's the sequence that you have to do for the electromagnets. Low, low, high, low. They don't have a beautiful library like I do, so I just have to go. What is the motor? There it is, ULN 2003, and I just tell it the pins, and then I can use it and say motor, go do this, motor, don't do that. Let me get rid of that code. So put that back. In Rust, we have this beautiful ticker with Embassy, the Embassy crates, and there's a time, Embassy time, and then there's Embassy Raspberry Pi. The Raspberry Pi crate is driving the time crate using the internal crystal clock at 1 megahertz, and we can use that to wait for things to happen. So in the C code, they're not waiting, so they use 0.2 watts more energy, and they have this jiggle thing which I've taken out. Where is there's a safety? They're all constants. where is their wait between steps? So here they're writing to the ports manually. There's 4 control pins, and then they're waiting. Delay, DT, delay time times 3. Where's delay time? 6. Oh, they've got 6 milliseconds. So in our case, with our code, we're just putting 1 millisecond. So rotate is here, and there's the milliseconds is there. So if I look at the help for that function, it is delay and it's a millisecond. 1 is as fast as the fastest I guess it can take. I tried putting it like just step, but the motor lights go crazy and it does nothing, which I will demonstrate now. 4 1 or IN 0 2048 motor dot step. And just steps 1 dot unlock because it's can return an error and we don't care about errors. And let me get rid of that. So it's just gonna like go hardcore, you would imagine, but it doesn't because let's run it. How do I run? Just does nothing. The lights just light up. All the motor's getting hot. You can see the lights here, they're just like full on. There's no delay, so it's just switching the magnets faster than the motor can physically move. So let's add our own delay in there. I'm not sure how to do that. Embassy time. Let me just pause it while I figure it out. So I've got it working, and that's just waiting a millisecond and turning the motor 1 step. I'm going to look at the code here. So it's like doing 2048 steps, and it's stepping and then waiting 1 millisecond. What if we change it to a microsecond? Is it going to crack out? Oh, the Cogs fan came out. Oh, you can't run after micros. I've got to change it. Micros. Done. And run and put the cog back in. That's not where it's not turning at all. Oh, it's making a high-pitched sound. Can you hear that? It's probably not good for the motor. Let's stop that and maybe change it to 100 micros. I'm going to say that a millisecond is probably the fastest the motor can go. Now it's making another sound. It gets no torque. I think that's what it is. It just gets no torque. Okay, let's change it to millis and let's do 6, which is what the original code had. It's going to be slower, but it probably has a lot more torque. It's not working. It's clicking. Why is it clicking? What's going on? It's trying to jump out of the cog. I think it gets more torque and it's slower. I don't know. How can I test the torque? I'll try and hold it. That's quite tough. Oh, okay. Okay, I'm just going to put it to 1 millisecond. Sorry for wasting your time. Let me pause it, put it back how it was, and test it. So I have one more thing to show you. I've put it back how it was. There's a ticker, which is a timer. Move to import, go to the ticker. The ticker is guaranteed, well not guaranteed, but it's within reason that even if your code takes like 30 seconds, it will wait exactly 1 minute between ticks. A server stream that heals every duration indefinitely. Very handy. So we have two timers going on here. One is the ticker, which goes every 60 seconds, and if we run this function every minute, we wait 60 seconds. And the $wait puts the Raspberry Pi Pico core to sleep. Maybe both the cores, I don't know. I think just both of them, one of them, because I never turned on the other one anyway. This is the Embrace Raspberry Pi init, which gives you all the peripherals, and then using the peripherals, you can say, oh, I want this pin, that pin, that pin, that pin. And in my code, because I've got this Raspberry Pi, which you can't see, turn that down. This is my debug Raspberry Pi, and it has them coming out of pins 16, 17, 18, 19. And this is my real Raspberry Pi, and that has it coming out of pins. See, they're soldered right in there. Terrible soldering, because this is the first time I've soldered since I was a kid. You can see the black scorch marks there. And that comes out of pins 2, 3, 4, 5 there. So this is the code. Oh, the other thing I wanted to show you was you have to turn the motor off, otherwise the lights stay on. So I'll just run that. So it does the rotate 1 minute, which is doing, and then the lights stay on. Because we didn't turn the motor off, and that draws 5 volts. So if you run it on batteries, it'll take a lot of power out. So we've got to turn the motor off. So that is my clock code. That's basically done. This thing, the 20 steps per minute, I just worked out by spinning the motor and watching how many steps it did. And I think that the speed actually affects it. So let me try with a different speed. Hang on. Okay, so my theory is that 48 steps, when you run at 1 millisecond between steps, is 4 minutes. So I'm saying times 60 divided by 4, which should give us a rotation around a whole hour. It's running. Don't run yet. I want to put it straight in the middle. Do it for Cogs for now. And I'll reset the Raspberry Pi. Where's the reset button? Don't see it. Okay. 1 second. I'll wait for the motor to stop spinning. Okay, here we go. Theoretically, hold turn. Let me hold the motor in and press run. So it should do a whole hour. Holding everything into place. The camera. Is it going to do a whole hour? Oh, crap, it stopped. Come on, baby. Going hardcore. So it should get exactly back up, but I think it missed a couple of notches, so it might be a minute short. 4 minutes short. So this is how I figure out how many steps to do per minute. You don't have to believe me, but I just ran it again and it ended up 1 minute short. So let's see what happens if I change it to a slower speed. Let's say 10 milliseconds. Bam. Conga run ready. Oh, it's already running the old one. I should give it like a 10-second timer. I'll give it a 10-second start after 5 seconds. Before we start it, the info waiting. And then info running, so we know what it's doing. Okay, stop. It doesn't actually stop the Raspberry Pi, of course, because the code's loaded. It's just like, yep, off I go. Let's get this in the middle. I'm looking at the camera view to see if I can. Okay, so run. It'll give me 5 seconds to get the cog in. Not enough time. Okay. I'll have to do it again. And stop and run and go. 5 seconds. Okay, so this is at 10 milliseconds between steps. Let's see if it makes a whole round off the clock. Oh, it's so slow. And it's so clicky. I think that click is to do with the layer lines. I will now pause the video so you don't have to wait and watch this. So this is the same code still running. It has gone more than a whole clock cycle around. I sellotaped the clock shut to hold all the clocks in place. So the speed does affect the number of steps it takes to get around the clock. Now we know. Okay, now to set my clock, I think that 2048 times 61 divided by 4 with 1 millisecond between steps will give me a whole 360 degree turn. So let's test it out. I have 5 seconds to put the clock in. Is that going in? It's not going in. So it should give me a full turn. Let's see. I'll pause it so you don't have to watch. Okay, we're nearly at the end. Will it be exactly 1 hour? That looks pretty close. Let me just have a look at myself. I think it's actually too far. Okay, so this is tricky. Let's just... So times 60 didn't give us the right amount of time. Okay, so now I'm going for 2100 instead of 2048. Let's see how we go at 2100. Stop, run, and this gives me 5 seconds to get the clock in. All the way around. I need that 5 seconds, see? Oh, it's already started. Okay. Stop. Start. 5 seconds. 1, 2, 3. Oh, what is it? We're in. I did it. Yay. So this should be 1 full turn. I'll pause and catch you up when it's about to finish. Here we go. Nearly at the end, and it should stop exactly. That's too far. Okay. Okay, I've set it to 2060. Let's give it a test. Ah, why did I keep on changing the wrong? Done. Oh, I'm good at putting it in now. Let's just give it a second. Okay, the moment of truth. Is it going to stop exactly at the top? Too far. Okay, I've set it to 2048 again. I'm assuming that before it must have missed a cog or something. 2048 sounds like a good number. It should give me 2048 divided by 4 times 60. I don't know why this is just my crazy math. I should do a full turn exactly. Here we go, moment of truth. Stop right at the top. Now, not far enough. Let's try 2052. So in the end, I looked at 513 times 60. So 513 steps per minute. And it did that pretty darn close. Rotation. Let's watch it again. And I will go down to steps per minute in the code and change it to... So it was 512 and now it's set it to 513. Which may hopefully give me a little bit more precision, but who knows, maybe when it's on a roll and it's going continuously, it does a perfect job. But when it's going by minute, it needs to start the cogs up, and that's going to stop right there. Oh, that's pretty perfect. I'm pretty happy with that. Let's have a look from my point of view. That's right in the middle. Good enough. Thank you for watching my video, and I will now put my clock back together and flash the code to it, to the other Raspberry Pi. So I fixed up the code, and now we're waiting, ticking every 60 seconds, and then we're running the every minute code, and the every minute code is going advancing and rotating steps per minute, and there's the steps per minute is 513. And I've got to get rid of that running because we don't need it every single time. Do we want to wait 5 seconds when we start it up? No, I don't think so. Okay, and then get rid of timer. Beautiful. So we'll just cargo build release. And I've set it up so that if we use debug assertions, which is non-release, it'll use pins 16 to 19. And if you use release, it'll use pins 2, 3, 4, 5. Now we've got to build the UF2, so we use elf to UF2, and then we've got to copy it, but first we've got to mount it. So you'll see on the Raspberry Pi there are 2 buttons. focus camera. One is debug and one is reset. Reset just starts the program again, and debug, if you hold it down, it turns the Raspberry Pi into a USB disk. So that's what I'm going to do. If I can find which one it is. Boot, this one. It says boot. So I'll hold that down, plug it in. Now I've got a USB disk, which I will mount. And then I just copy not convert, Rusty Clock UF2, which is that, and we're going to copy it to the Raspberry Pi, and that will unmount it and start running the code. So you can see that turned a little bit just then, but that's it. So the Raspberry Pi is ready to go. I'll put it back in the clock. I guess you probably want to see this. Get the other motor out. Get my cog back. What am I doing? The motor goes on here. All these cables, mamma mia, you just got to twist them up and get them out of the way. So I'll put the motor in first. Get this out of the way so you can see. And Raspberry Pi motor in. That's good. Is it not in? Why is it not? Was it going in? Take that off. Get it in. So there's a slot right in there. There for the motor wing to go in. And go in. I know it's not nice to see people struggling. Oh, there we go. It's in. Yay. And then wiggle that on. And this just slides in. And you'll notice that see these two slots? One's higher than the other, but you can't see the other. Which is perfect because this is one higher than the other. So that goes in like that. Zip. And what I do with all the wires is just pull them out, twist them up, and then go there. And then see there's a space inside the cover, which I thought was for a battery, but it's actually for all the wires to go in. Just pull them out the way of the motors. No, that's the space for the wires, sorry. Maybe this is a space for a battery. And get on, done. Easy peasy Japanesey. And now I do get cancelled for that. Just put the screws in. One in here. Dun, 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 dun. Not too tight, not too loose. Right here. If I can do it without looking. Okay, I need some torque. I need some push. It's important that the case holds the cogs in place. Otherwise they go click, 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 click and don't turn. I've pulled these screws in and out so many times. I'm amazed that the plastic's holding. They're tapping screws, so they actually drill a hole in the plastic. Looking good, and this one's still too loose. Brilliant. Is that falling apart? No, it's perfectly good. So now we can plug in the Raspberry Pi and it will just work. Here's the USB on the back. And just move 1 minute. Thank you for watching my video. Have a wonderful day and be happy.